Okay, hi everyone. So you had a question, please let me. Yeah, I said almost four. But if you have we roughly four. So if we have too many groups with less than four, then we will have more number of groups and it will be harder to grade and everything. So that's the reason that no, 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 that's not the case. But please do your best to do the project in a good quality. Thank you. Thank you. But if it is absolutely not possible to have four, then that's fine. But I prefer that you are four teams of four, so we will have not too many groups. Yeah, okay. This is the reason. Any other question? No. So, by the way, before we start, I have made announcements in the course link. Please look at that and also always check for the announcements in course link. Yeah, so the midterm exam for this course is October 26th, right? At the class time. And I will be there. The exam is open book, but messaging and ChatGPT and these are not available, not allowed. Hi. And so what else? Also, the assignment one has been posted and its deadline is mentioned in the Dropbox of the course link, so you can see its deadline. But oh no, there is no Dropbox for that because this assignment is not going to be graded, so there is no submission for that. But after the mentioned deadline on the PDF of the questions of the assignment, I will post the solution key so you can study that and check your answers. And also next week, although most of the next week is the reading week, but next week Thursday is not in the reading week. Therefore, we have a class, a statistical machine learning course next Thursday. Okay, please come. So we have a class next week in statistical machine learning. Although for deep learning, we don't have a class next week. And also, I've mentioned about the project proposals and teams, and there is a deadline for that. Also, in the last day of the course, you will present, and you have some time to apply the feedback and submit the final report. Any ambiguity or question? No? Okay. So that's one thing. And let's continue. Let's continue the lectures. Okay, so last time we talked about hard margin SVM, right? And we ended up at the start of the soft margin SVM. Now let's talk about soft margin SVM. So these were in the order of appearance, and proposal. So initially hard margin SVM was proposed, then soft margin SVM, then kernel SVM. So what is soft margin SVM? When the two classes, do you remember? SVM was a binary classifier, right? When the two classes are roughly linearly separable, but not exactly linearly separable. What do I mean? We have some points which make it. So for example, these are the two classes, but we have this point and this point too. If we ignore those few points, then they become completely linearly separate. But these points are pains in the neck, right? So roughly linearly separable. Yeah. Okay. So roughly linearly separable. In these cases, of course, hard margin SVM won't work, right? Will not converge because those few points will ruin SVM. Then the idea of Vapnik was this. Let's penalize those few points, but don't take hard on them. Dude, I don't know if I've talked to you about the soft penalty and hard penalty in this course, did I? No? So in optimization, we can have hard penalty or we can have soft penalty. For example, we can convert. Let me tell you a bit briefly about this. I think this is a good thing to know. So assume I have minimized f of x with respect to x subject to g of x is less than or equal to 0. Okay. It's a constraint optimization problem and it's hard, right? So what should we do? We can convert it probably to an unconstrained optimization problem. One of the techniques is that we say minimize f of x plus lambda g of x with respect to x. So we bring g of x as a penalty or regularization term, where lambda is the weight or called regularization parameter, and lambda is greater than or equal to 0 because it shouldn't convert minimization to maximization, right? And why does it make sense? Because if I minimize g of x, hopefully g of x becomes negative, right? Satisfying this constraint, right? So this makes sense, and also Lagrangian is in this form. This is called soft penalty. Why? Because although I'm minimizing g of x, but it might not become exactly negative. It might become 0.001, right? It's almost satisfies this constraint. So I'm saying that it's a soft penalty. Another way is that I say minimize f of x plus lambda indicator function g of x less than or equal to 0. So I bring the constraint as a condition of indicator function, where this indicator function, if g of x, if its condition is satisfied, becomes 0. Otherwise, if g of x is greater than 0, becomes infinite. So do you agree that infinite for minimization kills the optimization? If I want to minimize a function and that function becomes infinite, then it's completely opposite of minimization, right? So it kills minimization. What kills maximization problem? Minus infinity. Thank you. Right? So if we use indicator function, then I can satisfy this g of x less than or equal to 0 exactly. Because if it doesn't satisfy, even if it is too small but positive, this becomes infinite and it kills the optimization problem. This is called hard penalty, right? An example is that someone says, for example, an example in real world life. Someone says, I want to become a celebrity, for example, or something. So that if I don't become a celebrity, there are two cases. Either I kill myself, okay, or I don't buy myself pizza or laptop, okay? I don't buy myself laptop. So the first case, the first scenario is a hard penalty. If I kill myself, then there's nothing, right? But the second scenario is a soft penalty. I still harm myself, but with a little level, right? So as you see, this is for you to understand what soft penalty and hard penalty is. And as you see, hard penalty kills optimization problem. There's nothing worse than killing, right? So because we want to satisfy the constraint. This constraint. This was a constraint optimization problem. I wanted to satisfy that, right? So I want these to be equal to each other. So this is approximately equal. I want this to become an unconstrained optimization problem, which is easier to solve, but I want it to be exactly equal. For that, then I need to do this. Okay. Yeah, for satisfying some condition. And by the way, this in parentheses, this function, indicator function, is like this. It has two problems. First off, it's not smooth, right? It's not smooth. How do you take derivative? Also, it goes to infinity. It overflows in computer. How do you model it? How do you model infinity in computer? Right? So they approximate it by some function such as this. Okay, by some smooth function such as this. And they usually use logarithm function for that. Okay, there is a function which uses logarithm. That's why these methods in optimization are called log barrier. So first off, the indicator function is like a barrier, right? Barrier. Then if you use logarithm for that, it becomes log barrier. Log barrier methods. So log barrier methods is one of the famous methods. It's one of the algorithms for interior point algorithm. Interior point method. I think I have talked about this several times in this course. Interior point method is a generalization of Newton's method for constraint optimization problem. And for inequality constraints, it uses exactly the idea that I told you. And it approximates that using logarithm. Okay? Anyways, this was for you to understand soft and hard penalty. So, by what? Killing, murdering. So, does it make sense? Minimize infinite with respect to x. Does it make sense? So when indicator function becomes infinite, you will have such problem. It kills the optimization problem. Right?
It's invalid.
It makes it nonsense. You don't do what, so it kills it. Right? Because you're doing exactly the opposite of minimization. The function becomes infinite. So this was for you to understand hard and soft penalty. And now in hard margin SVM, it's related to that concept. It says that, okay, if I have such case, these classes, because of these 2 points, which are pains in the neck, these are not linearly separable. So my hard margin SVM never converges. Then Vapnik said, let's penalize these, but softly rather than hard. In this case, I can converge, right? Did you get it? So let's penalize them, but softly. And we'll see how. Okay. Did you get it in English? Now let's get it in mathematics. Okay. So therefore, we use soft margin SVM. As you see here, they are roughly linearly separable. If they are completely non-linearly separable, such as these, right? They're completely non-linearly separable, right? In this case, soft margin SVM will not work well. In this case, we need to use kernel SVM, which we'll see. But if they're roughly linearly separable with some bad points, we can say, okay, then we can use soft margin SVM. Okay. In this algorithm, so I'm not talking about this. In this algorithm, we penalize the few points which are misclassified by the decision boundaries, such as these ones. Let's call it nuisance points, whatever. So soft margin SVM adds n additional non-negative scalar variables, zeta I, zeta 1 to n. Okay, so it's adding several ones to the cost function and changes the optimization problem 11 to this equation 24. Do you remember optimization 11? If you ignore this part and also this part and this part, it becomes optimization 11. Let's go back and recall it because it was in the previous session. Let me find it. Equation 11. This was equation 11. Do you see that? This was the optimization the primal optimization problem for hard margin SVM. And as you see, we are modifying that to equation to, where was that? To equation 24 by having additional variables. And these variables are also additional optimization variables. So we have beta and beta 0. We now have zeta 1 to zeta n as additional optimization variable, right? So what, and this gamma, by the way, is the regularization parameter, which is greater than 0. It's a hyperparameter. Okay. Now let's analyze this. When zeta I equals 0, this optimization problem reduces to the optimization problem of hard margin SVM, which was equation 11. Right? Meaning that the point xi is correctly classified by the decision boundary. Right? Now, if a point xi is misclassified, right, zeta I greater than 0 for that point, zeta I, so basically, for misclassified points, zeta I becomes greater than 0. Okay? Therefore, the less the value of the zeta I, the more accurate the classification is, because the correctly classified ones have zeta I equals 0. So the less, the better. And now I think you understand why we are minimizing the summation of zeta i's, because we want them to be small. Ideally, they all become 0, ideally, if they are completely linearly separable. This is the reason for penalizing the summation of the zeta values. Okay, so we talked about this part. Addition of the variables zeta 1 to zeta n has loosened how hard SVM gets on the classification of the points. In other words, soft margin SVM says, don't take hard much on the points, right? Take it easy on them, right? Take it easy. So this is what we had. Now the constraints can be restated as this. So we have these and these. By the way, we have two n constraints, right? 2n. So what happens here now? I want them to become less than or equal to constraints, right? Because I want to use the method of Lagrange multipliers. So I can rearrange these to become less than or equal to 0. And also this, I rearrange it. I multiply the size by -1 to become less than or equal to 0. Now I form the Lagrangian. So the Lagrangian is a function of primal and dual variables. The primal variables are these, with zeta 1s also, zeta 1 to zeta n. Now I have two sets of dual variables, alpha 1 to alpha n for these constraints, and also lambda 1 to lambda n for the second set of constraints, right? Do you see what I'm doing? So this is the cost, right? And now sorry. This is for the n first constraints, and these are for n second constraints, right? Second n constraints. Agreed? Why?
Sigma.
Sigma, where do we have sigmas?
Gamma. And summation, that's same symbol.
Zeta, you mean?
Oh, that.
Zeta, I talked about it. We are adding zeta i's as a primal variables. So previously our primal optimization variables were beta and beta 0. Now we are adding n new optimization variables. And I told you what they are doing. If zeta I becomes 0, it means they are correctly classified. If they are greater than 0, it means that they are misclassified. So this is the Lagrangian, and Lagrangian, of course, became bigger this time because we have the cost function became bigger. We also have additional constraints, right? And these alpha i's and lambda i's are dual variables, also called Lagrange multipliers. So this is the Lagrangian that we had. I'm repeating it, right? Now the derivative of Lagrange, what should we do? We want to minimize the Lagrangian. Take derivative, set it to 0, right? So we should do it for all of the optimization variables. Let's consider the primal optimization variables. Take derivative with respect to beta 0 and zeta I, right? So with respect to beta, what happens? This term is quadratic with respect to beta. Its derivative is half times 2 beta. 2 and half cancel each other. It becomes beta. Agree? This term is constant with respect to beta. Goes away. This part, so I will have this, and this is linear with respect to beta. So it becomes xi, but I still have the summation. Why? Because I'm taking derivative with respect to beta, and here is xi. If I was taking derivative with respect to xi, it would be for a specific I, and the summation would go away, right? So I will have this. The other terms are constant with respect to beta, so they go away. We set it to the vector 0 because beta is a vector, right? Rearrange the terms. This gives us beta. Interestingly, beta is the same as hard margin SVM. You see that? Formula of beta was the same. Now, derivative of Lagrangian with respect to beta 0. What happens? The first term goes away constant. The second goes away constant. What about these terms? So let's see. I have beta 0 here, alpha I minus yi. This is linear with respect to beta 0, but still because of yi, I have the summation. So I have summation and alpha I, yi, because of both. And the minus goes behind the summation. Set it to 0, but scalar 0, because beta 0 is a scalar. We know the derivative of a scalar with respect to a scalar becomes a scalar. Set it to 0. As a result, we have this. I think we had these two, I believe, if I'm not wrong. Both of these we had in hard margin SVM. But now we'll have other equations in soft margin SVM. So taking derivative of Lagrangian with respect to zeta I. What happens? Zeta I, by the way, is zeta 1 to zeta n. So when I say with respect to zeta I, with respect to each of them, right? I mean with respect to each of them. And I know zeta I is a scalar, right? So derivative becomes also a scalar. Now let's take derivative with respect to zeta I. The first term is constant with respect to zeta I, goes away. The second term, can you tell me what is the derivative? So I have gamma here. What is summation of zeta I? Is derivative with respect to zeta I. So zeta I is linear with respect to zeta I. So its derivative is 1. But should I have the summation? The summation goes away because I'm taking derivative with respect to zeta I for a specific I. In other words, it is zeta 1 plus zeta 2 until zeta n. When I said that take derivative of Lagrangian with respect to zeta I, consider it for a specific I, such as zeta 1. Then all other terms will become constant. They go away. And this becomes 1, right? So the summation goes away. And I will have gamma. What about this part? So all of these are constant with respect to zeta I, but this. And what do I have here? I have alpha I. Let me clean this part. So I will have zeta I here, and I have alpha I here, also have summation. When I take derivative with respect to zeta I, it's for a specific I, so the summation goes away. And also its coefficient is alpha I. So it becomes alpha I, and minus is because of this minus. So I have minus, right? Now, what about this term? Take derivative with respect to zeta I. Again, for a specific I, summation goes away and its coefficient is minus lambda I. Set it to scalar 0, rearrange the terms, So it gives you this equation 27. We are gonna use that. Are you following? Yeah. Okay. Now, according to the method of Lagrange multipliers, for more information, see my optimization techniques course on YouTube. So we put all of these equations back in the Lagrangian. So I think the technique is understandable. We took derivative of Lagrangian with respect to the primal variables. We set them to 0. We found some equations. We put them back in the Lagrangian. As a result, the Lagrangian function becomes only a function of dual variables, right? So that function is called dual function, right? Do you remember? Okay, so this was a Lagrangian. Now I'm gonna put back the equations in the Lagrangian. But as it is a big term, big expression, let's do it term by term. Consider the first term. Half squared L2 norm of beta. So we know that the squared L2 norm of beta, recall preliminaries, is quadratic. It's beta transpose beta. What did I have in equation 12? Or 12 or 25? It's better to say, sorry about that. It should be 25. Okay? So if you put equation 25 back in the equation, then you will get this. So only xj becomes transposed because these are scalar, right? And I can rearrange the terms as we talked about it in the previous session. Then I will have these. So I'm bringing the summation here. And I know that xj transpose xi equals xi transpose xj. Now consider the third term, which is this. Okay? Consider this. So let's first simplify it. So I can multiply these terms to each other, and I also have alpha I here, so it breaks down into these two. Also, I can multiply alpha I to these two terms to get these two. Agreed? It gives me 4 terms, right? Now I can bring this beta transpose out of the summation. By the way, interrupt me whenever you have any question. Okay? So, but why can I bring beta transpose out of the summation? What? Which part is confusing to you? Let me re-explain that. You mean here? Okay. So let me re-explain this again. So consider first this times this times this. It gives you this, right? Now consider this times this times this. It gives you this. Now consider this times this, gives you this. Now consider this alpha I times this, gives you this. So we'll have 4 terms. Agreed? Okay. Now I'm gonna talk about this line. I can bring beta transpose out of this summation. Can you tell me why? Exactly, it's independent of I, which is the index of the summation. So I can bring it out, and I will have this. Also, likewise, I can bring beta 0 outside of the summation. C can be out of the summation, but for zeta I can't bring it. Alpha I also, I can't bring it out of the summation. So far clear? Right? Okay, now what are we doing? Now let's use equation 25. Beta here in this equation, because here I have beta transpose, right? I have beta transpose, so I can use that. So therefore, the first term becomes this, right? What about now? Consider equation 26. Summation of alpha I yi is 0. As a result, interestingly, this term becomes 0, right? And the other two terms are these. Because of this summation, we just found in the previous slide that is 0. The first term, so I have beta, I didn't drop that. So this summation is this. Beta transpose is this, according to equation 25. This is beta, right? I'm replacing beta with alpha. Okay. So basically what I'm doing in the next slide, I'm replacing beta with equation 25. And also I'm using equation 26 and maybe equation 27 in the Lagrangian function. I rearrange the terms here to get this, and the other two terms are as before, right? Agreed? As I told you, the Lagrangian, now let's put back the terms that we found together, and the Lagrangian becomes purely a function of dual variables or Lagrange multipliers. So we call that dual function, and we usually denote it by G. Do you remember? I talked about prime and dual functions in the previous session, right? So this is, therefore, if I put all of these terms that we found, it gives me dual function which has 6 terms. Okay. Let me clean this part a bit. These and these are the same, but this is minus, this is half. So I will have minus half. Okay. And now this term and this term and this term, all of them, they have zeta I. Factor out zeta I. Okay. And they also have summation. So the summation is here. Factor out zeta I, the rest is here. Agreed? This term is here. Did you see that? By the way, ask me if you don't part even a single step. And then what happens? Let's go back to 2 slides ago. Equation 27. What does it say? Gamma minus alpha I minus lambda I is 0. As a result, this is 0. This goes away. Interesting. So we'll have only these 2 terms. Do you see the beauty here? It's like we are dancing with mathematics, right? Right. It's very beautiful. So now we know that according to the dual feasibility in KKT conditions, for more information, see my optimization techniques course in YouTube, then the dual variable should be non-negative. Why? Because both sets of my constraints were in inequality constraints less than or equal to in minimization, right? As a result, their alpha i's and lambda i's should be non-negative for all I from 1 to n, right? So let's put back everything together. As do you remember, I said if we are minimizing the primal variable, it's equivalent to saying that we are maximizing the dual. The minimizing the primal function is like maximizing the dual function, right? So let's maximize the dual function subject to, we knew about these, right? Also, we had some equation for alpha i's, containing alpha i's, and that was equation 26. So let's use that as a constraint as well. This optimization problem is called dual optimization problem. Okay, right? Now let's compare equations 16 and 30. So this is equation 30, which is the dual optimization problem in soft margin SVM. Equation 16 was the dual optimization problem in hard margin SVM. Do you remember that, or let me go back because I myself might not remember it. Equation 16. Maximize. So can you remember this? Maximize something alpha I, alpha j, y I, y j, x I transpose x j plus c summation alpha I subject to summation alpha I, y I equals 0, alpha I greater than or equal to 0. Okay. Take a mental picture from that. Let's go back to where we were. The only difference is this line. The rest is the same. You see? The only difference is the n new constraints. Do you see that? So at the addition of the constants lambda I greater than or equal to 0 for all I from 1 to n. According to equation 27, what was that? This was equation 27, right? Gamma minus alpha I minus lambda I equals 0, right? Let's use that. We know that lambda I should be greater than or equal to 0, right? According to equation 27, gamma minus alpha I should be greater than or equal to 0. Why? Can't memorize these equations. This gamma minus alpha I minus lambda I equals 0. As a result, lambda I equals gamma minus alpha I. Do you agree? Do you agree? I'm rearranging. So when lambda I is greater than equal to 0, as a result, gamma minus alpha I should be greater than or equal to 0. So if we do that, we have this, rearrange this. As a result, alpha I should be less than or equal to gamma, right? So now, by the way, what is it saying? Can you tell me? Previously, we only had this part. It was saying that the alpha I should be greater than or equal to 0. Now it says in addition to being greater than or equal to 0 for alpha i's, they need to be less than or equal to gamma. So it puts an upper bound on alpha i's. The difference from hard margin SVM is that hard margin SVM, there was no upper bound on alpha i's. There was lower bound. In a soft margin SVM, we have both lower bound and upper bound for alpha i's. We have a range for alpha i's. Okay. So if we combine those two together, so if we combine this and this together, we can write it as this. Alpha I is between 0 and gamma. As a result, alpha I is sandwiched between 0 and gamma. So now we can write it in matrix form as before. We talked about it in the previous session, right? How to write it in matrix form. You remember? So let's put alphas next to each other as a vector alpha, yi's next to each other as vector y, ones next to each other as vector 1. S is a matrix whose ijth element is yi xi transpose yj xj. If as a result I can write all of these things in this form. What does this mean? This is generalized inequality for vector. For vectors, it means that this is element-wise. It is a vector, right? So basically, it means that each element is greater than 0 and less than gamma. This is what is it linear with respect to alpha? The cost. Is it linear? Is it linear? Is this part linear with respect to alpha? What is it? Quadratic. It's quadratic. So it's a quadratic programming problem. Also in hard margin SVM, it was a quadratic programming problem. We can solve it using optimization toolboxes, either using algorithms for quadratic programming or using interior point algorithm. Right? It is an iterative optimization problem. But interestingly, so as it is iterative, it needs random initialization, right? No matter which random initialization you start with, you will end up with the same solution. Why? Because it is a concave cost. And this quadratic programming has only one global solution. Okay? So it's like this. You start from here or here or here, you will end up always to the global base. Right? Interesting. The test phase of soft margin SVM is the same as the test phase that we talked about for hard margin SVM. Do you get it? When you don't ask me questions or when I get worried, does it mean that are you following me? Right? Don't hesitate. Just interrupt me if you have any question. Okay. So the test phase is the same as before. You remember we talked about test phase of hard margin SVM in the previous session. Now let's talk about KKT conditions to analyze soft margin SVM. So do you remember we had 4 conditions: a stationary condition, primal feasibility, dual feasibility, complementary slackness. For more information, see my optimization techniques course. So stationary condition says take derivative of Lagrangian with respect to the primal optimization variables. They need to vanish to 0. They must vanish to 0. We use that. Right? In the previous slides. Also, primal feasibility is obvious. It says that the constraints in the primal optimization problem should be satisfied. Right? It's more than obvious. Dual feasibility says that for the inequality constraints which are less than or equal to in minimization, the dual variables should be non-negative. So, and I know both of them were less than or equal to, and my primal optimization problem was minimization, right? So they need to be non-negative. We used all of these, I believe. The last thing, which is complementary slackness, is useful to analyze here for a hard soft margin SVM. So it says that alpha I, the dual variable, times its constraint, which was less than or equal to 0, must be 0. Also, lambda I times its constraint, which was less than or equal to 0, must be 0. So in other words, this and this, I have these 2 equations, right? For all I from 1 to n. Now let's see what they mean. So I'm repeating those 2 formulas here, those 2 equations here, right? So according to the primal feasibility, please take a careful attention at this. According to the primal feasibility, I'll have this, right? You remember we had this. If so, this must be greater than or equal to this part, right? I break it down into 2 cases. Either it's greater than this or equal to this, right? I can break down greater than or equal to into 2 cases, either greater or equal, right? So if it is greater, and the next case, if it is equal.
If it is greater, what happens? If it is greater, bring this left hand side to the right hand side. Basically means that this part is less than 0. Did you get it? Did you get it? So everything clear? So I brought the left hand side to the right hand side, and this means that this part is less than 0. If this part is less than 0, and we know that the multiplication must be 0, basically it means that alpha I must be 0, right? It means that the point is a non-support vector, because we know that for a non-support vector in SVM, alpha i's become 0. Do you remember that from hard margin SVM? In hard margin SVM, we said that support vector points, their alpha i's might be 0, might be greater than 0. For non-support vectors, their alpha i's must be 0. Do you remember? Here also, in this case, alpha I becomes 0, and it means that they are non-support vector. And they are outside of the margins. What were the margins? The margins were the ones which were. Do you remember the margins? In hard margin SVM, let's go back to that figure. We had, these were the margins with some equal distance from the boundary, right? And these were non-support vectors, and these were support vectors, okay? So basically, in that case, they are outside of the margin and they are non-support vectors. Okay, setting alpha I to 0 in the cost function of problem 30. Let's go back to problem 30. If you set alpha I to 0, what happens? The cost function of the dual optimization problem becomes 0, right? So basically, they don't have any effect in optimization. Similar to what we had in hard margin SVM. We said that hard margin SVM doesn't care about other points which are not support vector machine, not support vectors, right? Where were we? So it means that they don't have effect. Now the second case, if this equals the right hand side, so bring this to the right hand side, basically it means that this part is 0, right? When this part is 0, alpha I might be 0, might be greater than 0, right? Because we know that alpha I must be greater than or equal to 0. This part is 0. Alpha I times some 0 is 0. Alpha I might be 0, might be greater than 0. So alpha I will be greater than or equal to 0 according to equation 37, which said that alpha I must be greater than or equal to 0. It means that the point is a support vector, and now either on the margin or inside the margin, violating the margin. So the difference is here. Now in soft margin SVM, my support vectors are, some of them are on the margin, some of them are inside the margin. In hard margin SVM, all of my support vectors were on the margin. I didn't have any point inside the margin. In soft margin SVM, I allow some points to violate and come inside the margin. So I tolerate them, right? I call all of the points on the margin and inside the margin support vectors, okay? So now, according to the dual feasibility, I know zeta I is greater than or equal to 0, right? And if now I'm considering the second equation. If zeta I is greater than 0, so again, I'm going to break this down into two cases. Zeta I greater than 0 or equal to 0. As you see, I'm using cases inside case, so I'm using nested cases. In this case, I'm considering the two cases of this, right? I believe that this part, you should watch it 3 times at least, again and again, because it might be complicated for you to absorb it completely. Okay, so zeta I is greater than or equal to 0. Now break it down into these two parts. Zeta I greater than 0 or zeta I equal to 0. If zeta I is greater than 0, what happens according to this equation? Lambda I must be 0. Agreed? Agreed? Right? Now, recall equation 27. It was equation 27. We know that lambda I is this. I rearrange this term, it becomes this. And I just said that lambda I must be 0. So this must be 0. Rearrange the terms, alpha I must be gamma. Right? What about this case? Zeta I is 0. It doesn't violate the margin, but it is exactly on the margin border. By the way, when zeta I was greater than 0, I was violating the margin. I was inside the margin, right? If zeta I is 0, I'm not violating the margin, and I'm on the margin border. I know that lambda I must be greater than or equal to 0, right? According to my dual feasibility. If lambda I is 0, is like above case, and we have, because of this, if lambda is 0, I will still have alpha equals gamma. Okay, by the way, I will summarize this in the next slide. I know I have a lot of cases, I will summarize them. So if lambda becomes 0, I will again get this. However, when lambda I is greater than 0, what happens? According to equation 27, which was this, I rearrange it to this. I know that lambda is greater than 0, so this, rearrange it, alpha I must be less than gamma. Okay? Overall, in case there is zeta I equals 0, that is, the point is on the margin border, we have alpha I is less than or equal to gamma. Why? Because this, either this happens or this. Alpha I is equal to gamma, or alpha I is less than gamma. As a result, alpha I is less than or equal to gamma. I know we have a lot of cases and sub cases. Let's summarize them. In summary, even the summary is long. Okay. In summary, in soft margin SVM, support vector is defined as a points inside the margins, either on the margin boundary or in the margin. Okay? Agree? According to the constraint in equation 32, do you remember the constraint in the dual optimization problem? There was a lower bound and upper bound on alpha I. You remember that? You remember that? No? Let me go back. This. There was a range for alpha I, right? I have this range. Various cases might happen. If the point X, so 3 cases at least happen. The point is outside the margin, on the margin boundary, inside the margin. Let's consider them. If the point is a non-support vector that is outside the margins, then alpha I is 0. We analyzed that in the so the proofs were in the previous slide. Okay. If it is outside the margin, alpha I is 0. If the point xi is a support vector that is inside the margins, either on the margin boundary or in the margin, alpha I is greater than or equal to 0. Now we have 2 sub cases. It's either on the margin boundary or inside the margin. Let's see them. If the point violates the margin, it means that it's inside the margin. Okay. Then lambda I is 0 and alpha I is gamma. Proofs, previous slide. Okay. So consider these points, consider this figure. The points, these are non-support vectors, for example, their alpha I's are 0, right? But now I'm, in this case here, I'm inside the margin. For them, lambda I is 0 and alpha I is gamma, right? The point xi is either in the margin. Now, again, this breaks down into two sub cases. So the point is inside the margin. Now I have again two sub cases. It's either on its correct side or incorrect side. In other words, it's either classified correctly or it's misclassified. Right? Agreed? So if the point is either in the margin but correctly classified or in the margin but misclassified. Okay, now let's go back to the other case where the point is not violating the margin. It's on the boundary of the margin. It's exactly on the margin border. Then lambda I is greater than or equal to 0. Compare it with this. It might be 0, it might be greater than 0. But if it is inside the margin, it is lambda I is 0. Alpha I is less than or equal to gamma because of the upper bound on alpha I. In soft margin SVM, we have an upper bound on alpha I, right? So alpha I is actually between, so there is a lower bound too, between 0 and gamma. But I know that if I'm inside the margin, my alpha I is exactly gamma. I think this figure, which is bigger here in this slide, summarizes everything. Margin is determined by this. So basically, if you ignore some of the tolerated points which come out inside the margin, then if you ignore them, assuming that they never existed, this becomes hard margin SVM, and these are the closest points to the border, right? Now I'm tolerating some other points to become inside the margin. No, this is border, decision boundary. The margin is the closest distance of the points of the classes to the decision boundary in hard margin SVM. In hard margin SVM. In soft margin SVM, I'm saying that take it easy on the points. Let some of them pass the margin. And how is the margin determined? By optimization. Okay. As you see, in soft margin SVM, again, only support vectors contribute to the optimization problem because their alpha i's are greater than or equal to 0, right? So basically, if I move this non-support vector, nothing changes. But if I move it to get close to the margin and pass it through the margin, then the optimization problem changes, right? Agree? As a result, again, soft margin SVM is a sparse, like hard margin SVM. And sparsity is good according to Occam's razor and betting on a sparsity principle. So let's see this figure again. For non-support vectors like these, alpha I is 0. For support vectors which are on the boundary, alpha I is between 0 and gamma, right? But for support vectors which are inside the margin, alpha I is exactly gamma, lambda I is 0. Again, some of these violating support vectors are correctly classified, such as this. For example, this is violating, but on the correct side, right? And some of them are misclassified, like these. They are violating the margin, but they are misclassified, right? Now that we see the summary, you see it's easy, not too complicated. The proofs were a bit confused, right? Any question? No? An area around the decision boundary.
The dash line
Yes, the dash.
inside the area.
Yes. So do you remember? Forget this soft margin SVM. Do you remember hard margin SVM? Let's go back to that figure. Where was that? Do you remember this hard margin SVM? How was the margin determined? The distance of so this is the closest point to the other class. These 2 points are the closest points to the other class. Let's put a wall or the decision boundary between them with the same distance. Imaginary region, right? Yeah. So when there is a war between two countries, sometimes there is a region that for neither of the countries, right? What?
No man's land.
No man's
No man's land.
no man's land. So it neither belongs to this country nor to the other country. No man's land, right? Here, the region inside the margin is a no man's land. And I think now we found a good analogy. Assuming there is a war, give me a second. I think it's a good analogy. So here is a no man's land, right? In war. Hard margin SVM says if a soldier comes in the no man's land, kill him. Kill them. Soft margin SVM says don't kill them. Maybe put them in jail or give them soft penalty, right? Did you get it? Okay. I think it's a good analogy. Yeah, either kill them or in jail them. I don't know. Put them in jail. The advantage is that if you have these classes, consider these two classes. Are they linearly separable? No. If you solve the optimization problem of hard margin SVM, it never converges. It goes forever. But if you use soft margin SVM, it will find something between them, right? And I think, as far as I remember, the SVM, because we have two SVM functions in scikit-learn, not the kernel SVM one, the simple SVM is using soft margin SVM. Because you can see hard margin SVM as a special case of soft margin SVM. Okay. Any question? No? Classification of binary class. You can use it for classification of any data. So we are reviewing important fundamental classification algorithms, right? We covered regression, now classification. Any other question? No? Okay. Now consider completely nonlinearly separable classes, such as these or XOR classes. Right? These are very easy for neural networks, right? Because they are nonlinear. But for SVM, if you apply even soft margin SVM on this, it will not converge. Because I said for soft margin SVM, it needs to be roughly linearly separable. Also, this is very hard, right? So in these cases, we use kernel SVM. Now let me talk to you about kernelization in machine learning first, before we talk about kernel SVM. Linear algorithms cannot properly handle nonlinear patterns of data, obviously, right? When we have nonlinear data, such as I showed you the examples, right? Now assume my algorithm is linear. I'm a century ago, I have developed linear algorithms. Now I have nonlinear data. What should I do? How to resolve the issue? You tell me. I'm waiting for your answer. Up what?
Data existing methods for the non-linear.
One solution is RISC. Exactly, thank you. So update or modify the algorithms to become nonlinear. So they propose nonlinear algorithms to handle nonlinear data. Thank you. That was one approach. Another approach is what? Thank you. Yes, so do some transformation on the nonlinear data to hopefully become linear. So basically, you have data and algorithm. Modify one of them. Either modify the algorithm to become nonlinear or modify the data to become linear. Okay? Modification of data to hopefully become linear is called kernelization in machine learning. Okay? So we map it or we transform it. So the nonlinear data should be modified in a way to become more linear in pattern. This is called kernelization. So it becomes easier to process by linear algorithm. So do the transformation, then use the linear algorithm, right? And examples are kernel PCA, kernel FDA, and kernel SVM. We cover all of them in this course. Okay. So the second approach is called kernelization. Don't confuse this kernel with other kernels in other parts of the science. For example, we have a kernel of filter in signal processing, image processing, signal process. That's another thing, right? Kernel of filter basically means what filter you use for, what filter matrix you use for filtering, right? Or filter vector. Also, we have kernel, which is related in linear algebra, which is related to column space. Do you remember we talked about column space? So there are range and kernel also related to column space. We have kernel, I think, in graph theory, as far as I remember. So we have kernel in a lot of things. Maybe in quantum mechanics, they also have some kernel. So don't confuse all of them. They are different things, right? Here, I'm talking about this transformation, kernelization in machine learning. Okay? Agree? Did you understand? Yeah.
PCA and normal
Yes. So the difference of kernel PCA and normal PCA is that PCA is a linear method. It can handle linear patterns. Kernel PCA modifies the data and then applies PCA. By the way, when I say do the transformation and then apply the linear method, they combine this to become a new algorithm. They don't do it in two stages. They kind of combine these two stages to become one stage. Okay, we will see that. So yeah, so when we say kernel function, that's exactly the transformation that I talked about. So that which transformation do I apply on data? We have different transformations. We call them kernel functions. Okay. By the way, I think I'll talk about it. Yes, I will talk about. Okay. This figure shows what it is doing. So assume these non-linearly separable classes in the input space, in my space that I'm existing. Then I apply some transformation such as phi, right? A map. Then, for example, usually this transformation increases the dimensionality, usually, right? So it becomes like 3D. So I can bring these, pull them up, then they become linearly separable by a hyperplane, by a linear hyperplane, right? There exist two main approaches for kernelization in machine learning. One of them is kernel trick. I think you have heard of it. It's very famous, kernel trick, but I will explain it. Okay. The other one is kernelization by representation theory. Less people have heard of this. Okay, so it's less famous. There are two approaches for kernelization: kernel trick and kernelization by representation theory. Representation theory is a part of mathematics. Okay. An example of use of kernel trick is kernel SVM, which we'll see today. An example of kernelization by representation theory is kernel FDA, feature discriminant analysis. By the way, kernel PCA also uses kernel trick. Why do I cover these different kernel PCA, kernel FDA, kernel SVM in this course? To show you these two techniques. These are excuses to show you the techniques, right? Later, when you propose an algorithm, you can propose its kernel variants too, using these techniques, right?
You go back to previous two spot, ball on the. Yeah, this one. What if a deep neural network is gonna classify this task? If we train a new network.
A neural network will simply classify them. Because neural network is a nonlinear classifier. Because it has nonlinear activation functions. So it's a very easy task for neural network. After several iterations, it will converge to a good separation. Yeah, for example, it outputs higher numbers for this and lower numbers for this, for these regions. Right? So it's easy. As long as you have nonlinearity in your algorithm, it becomes easier for you to handle it. And by the way, in the deep learning course, I have explained why neural network is a monster, because you can see it as a stack of different algorithms. Let me tell you briefly here. If my layer is decreasing in terms of number of neurons, it's like a dimensionality reduction algorithm. If the number of neurons is increasing in the layer, it's like kernelization. So you have a stack of kernelization and dimensionality reduction. And also you have nonlinearity between the layers. So it becomes a monster. It's not just one algorithm. It's a stack of several algorithms, right? Okay.
The increase of the number of layers, will the running time and the cost increase exponentially, or?
So yeah, by the way, that's related to the deep learning course. But if I want to answer it briefly, when you increase the number of layers in neural network, you are adding the number of parameters also, the number of weights. So you have to increase your data, training data. Otherwise, I think you will, let me think, either overfit or underfit, but I should think about it. You will not have a good fit. So when you increase the size of network, you have to increase the data. For example, in ChatGPT, they have increased the network to become too big. They also have increased their data to become the whole internet data. Otherwise, they would not fit good. Running time will be larger. Less. It will take more time to be trained.
Exponentially? With the layer?
I'm not sure whether it's exponentially or linearly, but I'm sure that is going to increase. Okay, any other question? No? So here, as I said, we use kernel trick in kernel SVM. Let's see what it is. First, we need to define that transformation, that map of phi that I told you, right? So feature map or pooling function. We define this mapping phi from the space X is the input space to the space H, standing for Hilbert space. Usually the space that we're talking, which is higher dimension, is called Hilbert space, okay? When we are using the Hilbert space used for kernelization is usually called reproducing kernel Hilbert space, or RKHS, okay? I don't go into the theory much for that, but if you are crazy for theory, see, I have a tutorial on that. It's called, let me show it to you. Reproducing kernel Hilbert space, Mercer's theorem, eigenfunctions, Nystrom method, and use of kernels in machine learning. Tutorial and survey. This goes into the depth of the theory for kernels. As you see, it talks about Mercer's theorem and a lot of things, Nystrom method. These are related to the kernels, but it's not mandatory for this course. If you, I don't remember, but it took time. No. I don't remember the exact time, but it took time. So What I was saying that why do we call it reproducing kernel Hilbert space? Because it has some reproducing property. For proof, see that paper, that tutorial paper. Okay. So we use phi to transform data from the input space to the feature space, or that is the Hilbert space. So we usually call that space either Hilbert space or feature space. In other words, this mapping pulls data to the feature space. So this transformation is also called pulling. It's like I pull this from the input space to the Hilbert space. Okay. As a result, they call this pulling function. Okay. Or the feature, and this or feature map. Okay. Phi of x is called pulling function or feature map. This feature map is possibly a possibly infinite dimensional vector, because the dimensionality of Hilbert space might become infinite for some specific kernel functions. Okay, we will see that. So it might go forever. Phi 1, phi 2, right? Let T denote the dimensionality of the phi of x, the Hilbert space. The feature map may be infinite or finite dimensional. That is, T can be infinity. It is usually a very large number. The Hilbert space may have infinite number of dimensions. Okay. One technique to kernelize an algorithm is kernel trick. The other one is representation theory, which we'll see later. In this technique, in kernel trick, we first try to formulate the algorithm, formulas, or optimization in a way that data always appears as inner product of data instances and not a data instance alone. So what do I mean? Do you remember I said all of the machine learning is optimization? So you need to form some optimization problem. If you can form your optimization problem in a way that you always have x transpose x, not necessarily the same x's, it might be x transpose x1 transpose x2, right? But you need to have inner product between your data, x transpose x, right? Not a single x. If you have a single x, it will be ruined. Okay. You should always have some inner product between your data, x transpose x. If you only have x transpose x's in your optimization problem, in your formulation, you can simply use kernel trick. What does it do? It replaces x transpose x with phi x transpose phi x. Okay? And we call this phi x transpose phi x, which is the inner product between phi x and phi x, we call it kernel between x and x, denoted by k. So basically, it means that what is x transpose x? What does it do? Can you tell me? The inner product between two vectors. What does it do? What? Projection. But what does it? So consider these two vectors and these two vectors. How is their inner products different? This one is bigger, right? When the angle is smaller, the inner product is bigger, right? Basically, it shows the similarity because these two vectors are more similar than these two vectors, right? These two vectors also have negative inner product, right? Negative. Very large inner product, smaller, 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 right? They are becoming more different. So inner product is a measure of similarity. As a result, kernel is also a measure of similarity, but in the Hilbert space, okay? So what are we doing? We are basically saying that I'm pulling these data points to the Hilbert space, right? But let me calculate their similarity of pairs of points. And also I want these similarities to be kind of preserved there. So only the relation of transformed data points is really important to me, not the points themselves, right? X is not important to me. So as phi of x. X transpose x is important to me. So as phi x transpose phi x. Right? Okay. And as I said, it is called also reproducing kernel Hilbert space, or RKHS in short. So by the way, the matrix, it can be matrix. So we can have inner product between two matrices, x transpose x, capital X, right? Then it becomes phi of x now becomes a matrix also, because phi of x here was a vector, right? Phi of x transpose phi of x. This becomes a kernel matrix. So this was a scalar. right? But this becomes a matrix. When it becomes a matrix, we call it kernel matrix. Okay?
If we can. Then why you're taking the file?
No. The reason is that transformation. Because here in the input space, there are, for example, non-linearly separable. Hopefully, by this transformation, the pattern becomes easier for me to process. And how do we do that? We say that for this transformation, I don't care about the single points. I care about the relation of points. So I transform them also after transformation, the relation is important to me. I'm gonna talk about it. We'll actually, for many of the kernel functions, we don't know what phi it is. We know phi transpose phi. Yeah. Because actually the relation of points is important. Why is the single points important to me? The relation of points shows the pattern of data, whether they are linearly separable or non-linear separable, right? So kernel is n by n here if I'm using x transpose x or phi x transpose phi x, right? But what if I use kernel between two different points? By the way, what is kernel of x and x? It means that it's an n by n matrix whose every element, for example, whose ijth element is the kernel between xi and xj. Phi xi transpose phi xj. Did you understand? Okay, now consider two different points, such as xi1 transpose xij. We replace them with phi x1 I transpose phi x1j. This still gives me a kernel, scalar kernel. If I have between two different matrices, can you give me an example in machine learning? I have two different matrices. Each of these can be a data set. X1 is data set, X2 is a data set. Then X1 transpose X2 means the similarity, how much similar this data set is to this data set. The points of this data set. It can be X1 might be training data set, X2 might be test data set. Right? Yeah. So cosine similarity is related to inner product. So this is the formula. Do you remember this?
Yeah.
This is the formula of cosine. X transpose X normalized by the L2 norms by the lengths of the vectors, it becomes cosine of the two vectors, right? So as you see, this is in the numerator. So the larger the inner product, the larger the cosine. Okay. Here, if any of these x's might be x1 and x2. Which two lines?
Norm two. Norm two.
Which lines? I didn't get the question. Okay. Denominator. Okay, so what are no, I'm using inner product. I'm saying that inner product is related to cosine. I'm not saying that they are equal to cosine. If the two vectors are normalized, inner product is equal to cosine. The denominator becomes 1. So if basically cosine says that take the inner product between two vectors but normalize them. Your question is why cosine is normalizing. I can tell you. So no. So that don't confuse this. here I have a vector, I'm normalizing it by its L2 norm, so its length becomes 1. Basically, what do I mean? I have a vector like this, such as x. Its normalization brings here. So this becomes x over L2 norm of x. Basically, what is this? This is unit hypersphere. Its radius is 1, right? So cosine, as I told you, is cosine x1 and x2 is x1 transpose x2 over L2 norm of x1, L2 norm of x2. You can write it as this, x1 over L2 norm of x1 transpose x2 over L2 norm of x2. So basically it means that do the inner product between normalized x1 and normalized x2. Why does it do that? Because cosine needs to be between -1 and 1. That's the only reason. Did you get it? By the way, we will see that one of the kernel functions is the cosine kernel function. Okay, no problem. So I was saying that we can have two matrices, x1 and x2. Then it gives me, so I replace them with phi x1 transpose phi x2 in my kernel trick. So it becomes a kernel matrix, but this time rectangular with n1 rows and n2 columns. Agree? X1 here has n1 points and x2 has n2 points. For example, x1 is the data set with n1 points and x2 is the data set with n2 points. And I think I have said it several times. Here, I'm assuming my x1 and x2 have the data points column-wise, stacked column-wise, right? So basically, x1 can be d by n1. x2 is d by n2. What is the dimensionality of x1 transpose x2? x1 is d is the dimensionality of data by n1. x2 is d by n2. What is x1 transpose x2? n1 by n2. So the dimensionality go away in this way. And now I think you understand that where did the t go, which was the dimensionality of Hilbert space? Because the dimensionality goes away in phi x1 transpose phi x2. Right? But the only thing which matters in the kernel is the number of points, as you see, not the dimensionality. Right? Okay. Now let's review some of the well-known kernel functions. As you see, I haven't yet started kernel SVM. These are preliminaries of kernels. Well-known kernel functions. Linear kernel. So in linear kernel, phi of x is equal to x. So basically it means that remain in the input space. Don't do the transformation. But consider the relational points, right? So you replace x transpose x with x transpose x, basically doing nothing, right? So it becomes x transpose y. Now, can you tell me? So by the way, in this kernel, the feature map, the pooling function, is explicitly known. I know phi. Phi of x is x, right? Phi of x is x shows that data are not pooled to any other space in linear kernel, but in the we are in the input space. The inner products of points are calculated, right? If we use kernel trick, applying linear kernel is like doing nothing, right? Do you see that? Because x transpose x is replaced with x transpose x. So, but this happened because of I'm using kernel trick. If I use kernel if I kernelize my algorithm by representation theory, then linear kernel is not equivalent to not having kernel. So do you remember we have two types of kernelization? If I use kernel trick, linear kernel is not equivalent to not having kernel. If I use kernelization by representation theory, linear kernel has effect. So what can we conclude? In kernel SVM with linear kernel is equivalent to SVM. Kernel PCA with linear kernel is equivalent to PCA because these two use kernel trick. But what about kernel FTA? Kernel FTA with linear kernel is not equivalent to FTA. Okay, that's an important thing. Okay, I already explained this, I think. And another kernel is radial kernel function, is radial basis function, or RBF, also called Gaussian kernel. So what does it do? So it's this. Basically, it says the kernel between K and Y is calculated as this. EXP of minus gamma squared L2 norm of X minus Y. Right? Or you can write it in this way. So gamma here is 1 over sigma squared, and sigma squared is the variance of the Gaussian kernel, right? A proper value for this gamma is usually 1 over D, according to scikit-learn, okay? Where D is the dimensionality of data in the input space. Note that RBF kernel has also been widely used in RBF networks. For more information, see my deep learning course, okay? And kernel density estimation. What is kernel density estimation? Have you heard of it? If I have some data points, I can fit one distribution to that using maximum likelihood estimation and distance, right? However, what if I want to fit a mixture of distributions, such as mixture of Gaussian? I have two ways to do that. Either I use mixed expectation maximization. So for example, have you heard of Gaussian mixture model, GMM? If you don't know, it's nothing complicated. It uses expectation maximization for fitting a combination of several Gaussians, for example, to your data. This is one technique. The other technique is kernel density estimation. That also fits a mixture to data, a mixture of this. But how does it do that? Have you noticed that a distribution is like a histogram? But if you limit the bin sizes of the histogram to 0, so they become very fine bins, it becomes a PDF, right? This is exactly kernel density estimation. It limits the bin sizes to 0 in the histogram, okay? It's very interesting. So what were we talking? Okay, do we know phi in this kernel? Can I write it as phi transpose, phi x transpose, phi y? We can do that using Taylor series expansion, but if we do that, it goes forever. So the T here is infinite. Okay? Did you get it? Laplacian kernel, also called Laplace kernel, is similar to the RBF kernel, but it uses L1 norm rather than L2 norm, a squared L2 norm, right? So it's very similar, but rather than a squared L2 norm, it uses L1 norm. Hence, it is. Tell me, please. Whenever I hear L1 norm, what should I recall? Distance. Maybe Manhattan distance, but I'm not talking about that. What else do you remember? Sparsity, right? We talked about it in this course. So L1 norm imposes sparsity. So a Laplacian kernel imposes a sparsity. And this L1 norm of x and minus y is exactly what you said. It's Manhattan distance. What is Manhattan distance? Do you know that? Yes, it's one of the distance metrics. So consider, let me add a page. There is no space. In 3D, consider these 2 points. If you calculate the length of the vector connecting these 2 points, it becomes L2 norm, the Euclidean distance, right? But if you go in this direction first, then in this direction first, then in this direction first, one by one, sum them up, it becomes Manhattan distance. It's like using L1 norm between these 2 points. Okay. In 2D, I think it's more obvious. In 2D, it's consider L2 Manhattan distance of this point from origin. L2 norm is this, L1 norm is this plus this. Okay. And I think it's, why do they call it Manhattan distance? Assume you are in the Manhattan city and there are 2 points in this city. You have to go through the streets to reach the 2 points, right? By the way, we talked about it. So because do you remember the diamond? The diamond. See the regularization slide back. We had the unit ball of the diamond L2 norm and L1 norm. I said it's like a balloon touching the edges of the diamond. So did you get it? Okay. And it imposes a sparsity, as I said. L2 norm is more sensitive to noise. Can you tell me why? So RBF kernel is more sensitive to noise. This is L2 norm, okay? Consider for D equals 1. D equals 1. This is L2 norm. It's like a bowl, quadratic. For D equals 1, L1 norm becomes absolute value. You remember? Recall preliminaries. So it becomes absolute value like this. Now, a noise usually is outlier, right? It's either here or here. For example, if a noise is big, if a noise is small, we ignore it, right? If a noise is big and it's outlier, it's usually too much right to the right side or too much to the left side, right? What is the value of these two norms for a large noise? This is L1 norm. This is L2 norm. Which one is bigger? L2 norm. So L2 norm is more sensitive to noise. And I think even without this, it's obvious. In L2 norm, I have a squared L2 norm. You are squaring the noise. But in L1 norm, you're using absolute value of the noise. Whenever in a statistics, whenever you see a square, you should be both happy and scared. Happy because it is differentiable, it's a smooth. Scared for noises. Sigmoid kernel. It's this. It's actually the hyperbolic tangent. Hyperbolic tangent function applied to the inner product plus some intercept, right? And gamma is a slope, c is the intercept. Gamma is greater than 0. According to scikit-learn, gamma can be 1 over d and c can be 1. D is a dimensionality, right? The hyperbolic tangent is also used as one of the activation functions in neural network. The other one is polynomial kernel. It applies a polynomial function with degree delta. You understand what degree means in polynomial, right? X to the power of 1 is degree 1. X squared is degree 2. So degree delta, a positive integer on the inner product. So I have x transpose y with the slope and intercept to the power of d. Right? To the power of d or delta. Sorry, delta. Okay, to the power of delta. Okay. And again, according to scikit-learn, gamma can be 1 over d and c can be 1. These are different important kernel functions that I'm reviewing for you that you can use for calculating that kernel. Cosine kernel, that's just cosine kernel is exactly this, right? Here also, I think it's obvious because kernel was a measure of similarity, right? Cosine is also a measure of similarity of vectors. By the way, cosine kernel has been found to be useful for, I believe it was useful for face recognition. Okay, it was very good for face recognition, according to the literature I'm saying. And also, it's an angle-based measure, right? So similarity based on angle. Yeah, for face recognition. It's better than Euclidean distance for face recognition because you can use minus cosine as a measure of difference, right? Chi-squared kernel. Assume xj denotes the jth dimension of a d-dimensional point x, right? Chi-squared kernel denoted by this is defined as this. So xj and yj are the jth dimensions, features of x and y vectors. Gamma here is a parameter which is greater than 0, usually 1. The summation term inside the exponential without the minus is a chi-squared distance. Hence the name chi-squared kernel. Okay, we have a distance named chi-squared distance. By the way, in statistics, we have chi-squared distribution. We have chi-squared test. We have chi-squared distance. We have a lot of things, right? With chi-squared. Have you heard of test in statistics? It's one of the, to me, it was hard. One of the hard parts of the statistics. When you say test, it means that you have a hypothesis. You want to see whether this hypothesis is true or wrong. So sometimes in other fields of science, whenever we say that this is true, for example, we say, these are our accuracies, looks fine. The statisticians might say, no, how do you know that this is right? Test it. Okay. A famous test is t-test. We have also chi-square test. To me, that part of the science was hard. Okay. It might be easy for you. Depending on where you submit your papers. If the reviewers are very hard on you, they might say the tables of the results is not enough. You need to show the intervals of the what was it called? Confidence intervals and t-test and these things. Now we start kernel SVM. Should we have a break? Okay, let's have a break. Come at 9 and we continue with kernel SVM. Thank you. Okay, now we talk about kernel SVM. So kernel SVM was proposed by Vladimir Vapnik et al. Again in years 1992 to 1995. Okay, and do you remember equation 16, which we had in the dual optimization problem of hard margin SVM? Do you remember that? This was it. This was the dual optimization problem that we had, right? Interestingly, it has only xi transpose xj. Therefore, I can use kernel trick, right? This is the reason why we can have kernel SVM, because I have xi. Do you see a single xi or a single xj? No? Do you see that? Do you see that? You don't see that, right? You don't see xi or a single. So I can use kernel trick. Therefore, I replace xi transpose xj with phi xi transpose phi xj, or kernel of xi and xj. It becomes this. So basically, this part has changed, right? And the rest is as before. Now, what is this? Again, this is quadratic with respect to alpha. This is a quadratic programming. I only change xi transpose to xj to kernel of xi and xj. The rest is as before. Optimization variable was alpha I. So it's still quadratic with respect to alpha I, right? It's a quadratic programming problem. Use interior point method or optimization toolboxes to solve it. The only difference was that this one page is kernel SVM. Did you see that? Okay. So note that it is possible to use kernel trick in soft margin SVM too, right? However, it is not required. Why? Why don't we need to use kernel trick in soft margin SVM? Because when we use kernel trick, it already separates hopefully it already separates the classes to become linearly separable. So why do we care about tolerating some points? Right? Kernel SVM makes it easier for us to separate the classes. So we don't need that. Analysis of KT conditions of kernel trick is the same as we did for hard margin SVM. Right? Now let's talk about kernel SVM versus neural networks. Because of usage of kernel function, kernel SVM can handle non-linearly separable classes, right? Also, we know that neural networks are nonlinear because of nonlinear activation function. So both can handle nonlinear pattern of data, but they have benefits over each other, pros and cons. Kernel SVM was winning because there was a competition between kernel SVM and neural network, right? So it was winning the competition with neural network in 1990s and the start of the 21st century. This time period is referred to as the winter of neural networks. Okay. The reasons for overcome of kernel SVM against neural network are these. Kernel SVM is mathematically sound and solid. It's more theoretical than neural network, right? And people love theory. Kernel SVM was able to perform nonlinear classification, although neural network also could do that. At that time, multi-layer perceptron neural networks could not become too deep. I have explained the reasons in deep learning course, because when we increase the number of layers in neural network, we'll have vanishing gradients or explosion of gradients. And they could solve it later using first restricted Boltzmann machines, later using regularization techniques such as dropout and ReLU activation function later. But at that time, we didn't have these things, so we couldn't make it deep because of gradient vanishing and gradient explosion. So for these reasons, kernel SVM was winning. But there is a problem with kernel SVM. There are several problems. I don't know if I've explained them here or not. Yes, kernel SVM required choice of kernel function. Which kernel function do I use? Let me tell you one thing. When you propose an algorithm, try not to give too much freedom to the user. Otherwise, giving freedom to the user is a flaw of your algorithm. When you give the user freedom, you give the user responsibility, and the user doesn't like to have responsibility. Okay? This is an existential problem in existential philosophy. There are 4 things in existential philosophy which are very important. One of them is death. One of them is meaning of life. One of them is freedom and responsibility. There was another one. I forgot. What was the 4th one? So death, meaning of life, responsibility, freedom. I can't remember. I'm getting Alzheimer. Okay, so anyway, so there are 4 things. If you want to read more about these, there is a book by Erwin Yalom named Existential Psychotherapy, I believe. Existential Psychotherapy, I guess. Yes. It's a very famous book talking about these 4 things in existential philosophy. So anyways, don't give freedom, because freedom brings responsibility. Even in real life, sometimes people don't like freedom much because it brings responsibility. So choice of kernel function is a flaw. Also, calculation of kernel function is time consuming. So its time complexity and space complexity are awful, because it needs n by n rows and columns, right? Too many rows and columns, especially for large big data. When you have big data, you have too many data points, right? N is large. So your kernel matrix becomes big, memory error. Also, calculation of this kernel function, kernel matrix, is time consuming, right? Another one is that the problems of gradient vanishing and explosion were resolved using various techniques later for neural network, such as initialization of weights by a restricted Boltzmann machine in the year 2006, ReLU activation function in the year 2011, and dropout technique in year 2014. So gradually, neural networks won the battle against kernel SVM. But at least for a period, kernel SVM was better, and even any paper which had neural network would get rejected. If you were proposing papers in the year 2000, you couldn't write a paper in neural networks. It would get rejected in high quality conferences. Okay. More notes. For multi-class, sorry. Yes. For multi-class classification, we can consider every pairs of classes as binary classification, because SVM and kernel SVM were for binary classification. But if I have multi-class classification, I can consider pairs of classes as binary classification algorithm, right? So a multi-class classification can be considered as a set of binary classification problems. SVM can also be used for regression. So far we talked about SVM for classification. SVM can be used for regression too. It's called support vector regression, or SVR. Reference 31. It has also been used for let me think. Yes, for outlier detection, or also called anomaly detection. Its name is one class SVM. Okay. Reference 32. Here we went through SVM and kernel SVM for binary classification. Let's see SVR. What is SVR? Its formulation is this. Equation 54. Very similar to the formulation of SVM, but let's see what it is doing. Consider this left figure. What am I doing in regression? I want to assume this is SVR, so it's a linear regression method. It fits a line, okay? I have several data points, cross points. I am fitting a line. Which line is the best? The line which goes through the points. So it's the other way around. In SVM, I want to avoid the points. In SVR, I want to fall on the points. That's one thing. And my margin should include the points, not avoid the points. Did you understand? So I have margin around my fitted line, which should include the points. And of course, some of the points will be included, some of them, which will be outlier, will be non-support vectors. Those non-support vectors, I don't care about them. Again, this is a sparse algorithm. I only care about support vectors, which are the inliers, right? And what are these two constraints doing? Basically, it says yi. What is this? Beta transpose xi plus beta 0. That's the fitted line, linear regression, right? Predicted label. What is yi? The actual label. So the actual label minus the predicted label should be less than epsilon. Also the other way around. The predicted label minus the actual label should be less than epsilon. In other words, the absolute value. These two can be summarized in this one inequality. The absolute value of the predicted label and the actual label should be, their distances should be less than or equal to epsilon. Right? It makes sense. And its formulation is very similar to SVM. So you can solve it using similar to SVM. I think one of, as far as I remember, one of the co-authors of SVR was Tipshirani from Stanford University. Have you seen his citations? It blows your mind. He's one of the godfathers of AI. Okay. One, by the way, theoretical godfather. Okay. One class SVM, for that, see the right-hand side figure. Kernel one. So basically, what does it do? Because usually we use kernel one class SVM. So it finds a non-linear boundary, decision boundary. Do you agree that I can see outlier? What do I do in outlier detection? I detect outliers, right? Or in other way around, I detect the inliers. Doesn't matter. Okay. So basically, I can see it as a binary classification where I'm separating inliers from outliers. As a result, you have one class SVM. What do I mean? I only have one class, which is inliers. The other part of the other regions of the space are outliers, right? That's exactly the main idea behind one class SVM. So SVM and kernel SVM scikit-learn. This is SVM in scikit-learn. We have kernel SVM in scikit-learn. We have linear SVM. So let me open these. If I can. I think I need to Google them. Okay, just give me a sec. SVM, sklearn. So we have linear SVM. Do you see these? Okay. We have linear sklearn.svm.linear svc. We also have sklearn.svm.svc. Linear svc is linear SVM. SVC is kernel SVM. Okay. And as I have said in this slide, linear SVM is much faster than kernel SVM. Much faster. For example, if kernel SVM takes minutes, linear SVM might take several seconds. Okay. In scikit-learn. Sklearn itself recommends using linear SVM for large data sets. But of course, it's a linear classifier, right? But kernel SVM is... so basically, what do I mean? Assume you want to do linear SVM. You have two choices. Either use linear SVM library or kernel SVM library with linear kernel. Which one do you do? Of course, linear SVM is faster. Okay. Tutorial page for SVM in scikit-learn is this. Okay. By the way, as you see here again, we have some parameters. If we zoom, we have some parameters. We have C, we have the kernel function, we have the degree, if gamma, all of these coefficients that we talked about, right? Their names might be different, but these are the parameters that I talked to you about. We also see, for example, kernel, degree, gamma, coefficient, this tolerance in soft margin SVM, tolerance. So what does it mean? That it is kernel SVM, but it has tolerance. It means that they have kernelized the soft margin SVM. Okay, that's fine. You could do that, right? I'm not sure whether it supports GPU or not, but it depends on whether calculation of kernel function can be parallelized or not. I think you can. Elements are not necessarily related to each other when you're calculating the inner products. So, by the way, it has fit. Where is it? Yes. So we have fit, which is train, predict, which is test phase, right? As before. So also have linear SVM. Okay, let's continue with the next thing. SVM is over. Any question? By the way, acknowledgement. I forgot. For more information on KKT conditions, dual problem, method of Lagrange multipliers, etc., refer to my optimization techniques course at the University of Guelph, whose lectures are on my YouTube channel. For more information on, again, these KKT conditions and optimization, you can see this tutorial paper. That I have a tutorial paper on optimization. KKT conditions, first order and second order optimization, and distributed optimization tutorial and survey. It's a very long tutorial. Basically, I think I covered the whole tutorial plus some other things in that semester. So that became a whole course. Okay. For more information on kernels, see our tutorial paper also on kernels. I told you once, reproducing kernel Hilbert space, Mercer's theorem, eigenfunctions. By the way, eigenfunctions are also used in quantum mechanics. Nystrom method, and also it's widely used in machine learning. It was first used in machine learning by Yoshua Bengio. You know Yoshua Bengio? Yoshua Bengio is one of the godfathers of AI. He's in Montreal, okay? He used eigenfunctions for machine learning too. So reproducing kernel Hilbert space, Mercer's theorem, eigenfunctions, Nystrom method, and use of kernels in machine learning, tutorial and survey. By the way, Nystrom method is for approximating the kernel, okay? Approximating the kernel. Some slides of this slide deck are inspired by teachings of Professor Ali Qudsi at the University of Waterloo Department of Statistics. No, he wasn't my supervisor, but I have worked with him in writing the book. Who? No, mine not. No. Have you seen others? It's mine is not.
You can apply like a US passport because of you have high citation.
Thank you very much. I appreciate it. So these were the references. Any question? No. Okay. Let's go to the next topic. What was the next topic? KNN, I guess. K-nearest neighbors. Okay. The next topic is K-nearest neighbors. Initially, you might think it's very easy, it's childish, but at the end of the slide deck, it becomes a bit more complicated. So you don't get bored, okay? Consider the data set x1 to xn, each of which is d-dimensional, okay? Some data points are close to each other and some are far from each other, right? In the d-dimensional Euclidean space. We can calculate the Euclidean distance between every pair of points in the space. Do you agree? So we can calculate the Euclidean distance between every 2 points. Now consider a point xi. We can calculate the Euclidean distance of all points of the dataset except itself, because distance of a point from itself is 0, right? From this point. So consider, so these are the Euclidean distances of all points from that xi, right? Do you agree? I calculate them. I calculate, consider one of the points xi. I can calculate the distances of all of the points, each of the points from this point. Now I sort these distances in the ascending order. By the way, I can use any distance metric, such as Euclidean distance, right? Then I sort them in ascending order from smallest to largest. And keep the k smallest distances, hence the name k nearest neighbors, okay? K is some hyperparameter, like some integer, right? The corresponding k points with the smallest distances from xi are called the k nearest neighbors, or KNN of xi, okay? So far clear? K is a hyperparameter, positive integer for the number of neighbors. Agreed? We do this procedure for n points of the dataset, for all of the points. So for each point, I will have k neighbors, k nearest neighbor. Now consider a graph whose vertices are the indices of the points, 1 to n. So a graph has some vertices and some edges, right? The vertices are the indices of the points. 1 to n, and an edge from vertex j to vertex I exists if xj is one of the k nearest neighbors of xi. So if, consider xi, if xj is a nearest neighbor, is one of the k nearest neighbors of xi, then I have an edge from vertex j to vertex I. Did you get it? No.
Are we creating a polygon in the graph so that we are comparing the distance of the point I with the point J?
So I'm saying that calculate the k nearest neighbors of all of the data set, as I said. Then I'm forming a graph. Every vertex represents one of the data points. Okay. And I can calculate. I draw a line, an edge from vertex j to vertex I if xj is one of the k nearest neighbors of xi. Okay. Such a graph is called KNN graph, k nearest neighbor graph of the data set. Okay. Do you understand?
So if J is one of the neighbors of point I, so can it be said that when they're considering a lot of data points, they are enclosing them in by drawing edges of points that are nearby?
I didn't get it. Can you tell me again?
I'm saying J is the nearest neighbor of point I, and we are joining them. We are creating an edge by joining the point I with point J, because J is very near the I, right?
Okay.
If we do that for very large sets, are we enclosing all of them? That are we plotting? I mean, what is the point of joining the vertices?
What is the point of that?
What is the point of creating edge?
It's because I want to represent the data set, the nearest neighbor data set as a graph. So you can have k nearest neighbor matrix. You can have k nearest neighbor graph. Here I want to represent it as a graph. Then I can represent the edges to, I want the edges to show the neighborhood, whether they are neighbors of each other or not. By the way, can you tell me whether this KNN graph is symmetric or whether this k nearest neighbor matrix is symmetric? I mean, if xj is for example, one of the k nearest neighbors of xi, should xi also necessarily be one of the k nearest neighbors of xj? Not necessarily. Can you give me a counter example?
Like say what if it's not linear? So that would be normal.
I think I understand what you're saying. Yes, so I can show it you with simple counter example. Simple. Consider 3 points. 3 points. Data set of 3 points. And k is one nearest neighbor. So consider this point. This is xi, this is xj. One nearest neighbor of xi is this, right? But one nearest neighbor of xj is xi. So one nearest neighbor of xi was not xj, but one nearest neighbor of xj was xi. Did you see with this simple counterexample? We just proved that it's not symmetric. Okay, so the graph is also directed. The edges are directed. Okay. Graph directed. Not symmetric, not necessarily symmetric. It might be symmetric, right? Not necessarily symmetric. Now, let's talk about adjacency matrix. Consider a matrix A, n by n. N was the number of data points, right? Whose ijth element is this. If j is one of the k nearest neighbors of xi, if xj was one of the k nearest neighbors of xi, it's 1, otherwise it's 0. Okay, of course, it's not symmetric. And it's called adjacency matrix because it says whether they are adjacent to each other or not, neighbor of each other or not. Usually, the main diagonal of the adjacency matrix is 0 or ignored. because we do not consider every point to be its own neighbor. And this is not necessarily symmetric. If k is much less than n, what does it mean? The number of neighbors is much less than the number of data points. Then the adjacency matrix is very sparse because it has a lot of zeros, right? Because it's an n by n matrix. We can have the adjacency matrix between two data sets with sizes n1 and n2. In this case, the adjacency matrix will not be a square matrix. It will be n1 by n2, right? Note that one may define the adjacency matrix to be n by k. So there's another way to form the adjacency matrix, where every row lists the indices of the k nearest neighbors of xi. Did you understand? So every row corresponds to one of the points, and every column corresponds to the neighbors of those points. There is another way to do it. Okay. KNN for machine learning now. So far we talked about KNN. Now for machine learning. KNN can be used for machine learning tasks, such as regression or classification. For every input x, we find the k nearest neighbors of x among the training data points, right? The average or sum statistics of the labels of the KNN is used as the estimated label for the point x. This point x, the input x, can be train point or test point, any point. Any point in this space comes, I want to predict a label for it. And the labels are continuous, not necessarily discrete. So I have some training data set in this space, some training data points with their labels, and the labels are continuous regression. Then consider a data point, a test data point, or a training data point, some point in this space. I take the k nearest neighbors from among the training data points, right? Not among the test data points, among the training data. I see their labels, then I use some summary statistics of these labels, such as mean, such as median, such as anything, right? Take the mean of the labels, take the median of the labels, take the mode of the labels, whatever. Of course, for regression, we usually don't use mode because the labels are continuous. We usually take mean or median. As you see, this is a regression method, and this is a non-linear regression method. It's not linear. Okay. Now we can use it for classification, but for this time, I do the same procedure, but rather than taking the mean of the labels, I do the majority vote. I have the labels of the training data points, and they're discrete and finite, right? They're the labels of classes. I see for a point its nearest neighbors among the training data points, and I see their class labels. The majority class label shows the estimated class label for that data point, right? And as you see, KNN for classification partitions the space, similar to what LDA does. But of course, it is a nonlinear partition, right? KNN for regression or classification does not have any training phase. Do you see that? It's an algorithm which doesn't have any training phase. So what does fit function in scikit-learn do for KNN for regression or classification? What does it do? The only thing which it does, it accepts the training data points. It gets the training data points from you to know where they are. That's it. Doesn't have any training phase. It only accepts them and puts them in the memory. Okay. Then it uses them in the test phase. The KNN classifier partitions this space, as I told you. The smaller the k, the more variance of the decision boundary of classes. If you don't believe it, try it. Increase k, the decision boundary becomes smoother. Decrease k, the decision boundary oscillates. Becomes very complicated. Therefore, the small k leads to overfitting. Why? Because overfitting had high variance. We talked about it. In general, larger k in KNN classifier or regressor results in less overfitting and better generalization. However, there's a trade-off. Larger k has more computation. Right? Yeah. If I can find an example, hopefully I hope it's. Let me try to. Oh yeah. This is an example. This, my cursor is on the partitions strings. Okay. So now let's make it a bit more complicated, not to get bored. Okay. Kernel KNN. We can kernelize KNN. Had you heard of that? Kernel KNN for machine learning. Let phi be the pooling function from the input space to the feature space, reproducing kernel Hilbert space. We talked about it, right? Now recall the kernel trick. X transpose X, I can map it to phi, X transpose phi, right? The squared Euclidean distance between points in the feature space is this. Assume this is 2. The squared L2 norm, what would it do? Anything, a squared L2 norm, according recall preliminaries. Benjamin, a squared L2 norm is Benjamin transpose Benjamin, right? So let's see. This Benjamin transpose Benjamin. I apply transpose on these, and then I multiply the terms to each other. I will have 4 terms. This. Right? Did you understand what I did? Yes? Okay. Now, interestingly, let me think. Interestingly, these two, can I write this as phi xj transpose phi xi? X transpose y equals y transpose x, right? Because they are a scalar. So phi xi transpose phi xj equals phi xj transpose phi xi. So these two are the same. I write it as -2, one of them. Right? So I will have these 3. What is this according to the kernel trick? What is this according to the kernel definition? This is kernel between xi and xi. This is kernel between xj and xj. This is -2 kernel between xi and xj. Agreed? I just proved that the squared L2 norm, the squared Euclidean distance between points in the Hilbert space is kernel of that at itself. So kernel of the first by itself, kernel of the second by itself, and -2 kernel between them. Did you see that? I just proved this, equation 3. This is a very important equation. It was first proposed by Sholkov. Who was Sholkov? I think I talked about him. Sholkov is the god of kernels in machine learning. The godfather of kernel in machine learning is Sholkov. Bernard, I think, Sholkov. He is in Max Planck Institute in Germany. Okay. He's very good. his lab is focusing on kernels. So he proved that and he published it in NeurIPS. What? What? No. I'm saying that Ben transpose Alex is Alex transpose Ben if Ben and Alex are vectors. Because Ben transpose Alex is a scalar. Alex transpose Ben is also a scalar. Recall preliminaries we talked about. So did you get it? Okay. So that's important. Now I think you guess what I'm gonna do. I'm gonna use the distance in the Hilbert space for calculation of k-nearest neighbors. For k-nearest neighbors, I need to calculate the distances. Rather than calculating distances in the input space, calculate the distances in the Hilbert space. And then sort the distances, form the k-nearest neighbor graph or adjacency matrix, and then you can use it for classification or regression, right? So this is called kernel KNN. And we can use it for classification or regression. Distance metric learning for large margin nearest neighbor classification. K-nearest neighbors or KNN classification is highly impacted by the distance metric utilized for measuring the differences between the data points. So if you use Euclidean distance or Manhattan distance or different distance metrics, the result would be different in KNN classification or regression, right? Then what is the best distance metric to use? So recall Mahalanobis distance. I talked about it. Do you remember? Do you remember Mahalanobis distance? I talked about it in the previous session, I think. Don't you remember? I talked about it. Okay, so let me talk about it again briefly. Consider these two classes, x1 and x2, and a test point x. Just use the distances of the x from the means of the two classes. Euclidean distance says that x belongs to class x1 because its distance is lower, right? This is smaller. But our eyes, our brains show that x must be in class x2. So a scientist named Mahalanobis said, let's scale these distances so they match our understanding. Here Euclidean distance is making a mistake. So he proposed a Mahalanobis distance, which says that rather than saying, so we are using x minus mu, right? Mu is the mean of the class. What was the Euclidean distance between x and mu? It was x minus mu transpose x minus mu. Do you remember? This was Euclidean distance. Mahalanobis said rather than this, let me use x minus mu transpose sigma inverse x minus mu. And sigma is the covariance matrix of the class. Okay. So I'm using this twice, for once for this class and once for the other class, and then comparing the distances. But why do I have sigma inverse? The reason is that here, my class 2 is more spread, has more variance. So I should scale down its distance, right? I should make it smaller. This is a small class, so I should make it bigger, the distance bigger. Then, if I do that, this distance becomes smaller than the other distance, right? As a result, I use sigma inverse because the bigger the variance, the smaller the distance should be. Then later, scientists said, why do we use sigma inverse? Let us use a general matrix M. A general matrix M. What, can we use any M? No, it needs to be a distance metric, right? For this to be a distance metric, it should satisfy triangle inequality. Recall preliminaries, right? Also, it needs to be convex. For this to satisfy triangle inequality and to be convex, M must be positive semi-definite. What do I mean? Its eigenvalues must be non-negative. I think the reason is obvious. Why? Because if you take derivative twice from this metric, ignore the square root. Assume I'm using squared distance, okay? If you take the derivative twice, you will end up with matrix M. When the second derivative or Hessian is positive semi-definite, it means that it's facing up. When it is negative definite, it's facing down. For this to be convex, the Hessian must be positive semi-definite. So M must be positive semi-definite because Hessian here is M. Did you get it? Did you really get it or no? Let me add a page. So I have x minus mu transpose M x minus mu. This is my squared distance, right? Take derivative once with respect to x. What does it become? 2m x minus mu is quadratic, right? Take derivative again. Second derivative. Comes 2m. Ignore 2. 2 is not important, right? So for this to be convex, the Hessian must be positive semi-definite. So M must be positive semi-definite. Agreed? As a result, if we replace sigma inverse with general M, which is positive semi-definite, we call it generalized Mahalanobis distance. Okay, and we denote it by this. A squared norm with M subscript M between xi and xj. It's this. Okay. Can I write M as LL transpose? Can I do that? I talked about all of these last session. I'm just repeating them. Can I write it as LL transpose? Yes, because write the eigenvalue decomposition of M. Right? Eigenvalue decomposition of M. Can I write it as U delta half U transpose? Yes. Why? In general, am I allowed to write any matrix as matrix to the power of half times matrix to the power of half? No, I'm not allowed to always do that. What if one of the elements is negative? I'm only allowed to do that if all of the elements of the matrix delta are non-negative, right? Here, I know that my delta is diagonal first, and the diagonal elements are non-negative. Why? Because I just told you it's a positive semi-definite matrix. So its eigenvalues are non-negative, right? So I can write it and then take this as L, and this becomes L transpose, right? So basically, I replace M with LL transpose. Now I apply this L to the left-hand side and L transpose to the right-hand side of the parentheses. I will get this and this. Basically, what is this? Benjamin transpose Benjamin. A squared L2 norm of Benjamin, right? What is this? Can you tell me? What is L transpose X? Recall preliminaries. What does L transpose X do? I think you are tired. I will finish it now, but let me, before finishing, can you answer what is L transpose X do? Remember? It's linear projection onto the column space of L. I've seen it a lot, right? So basically, I just proved to you that what is generalized Mahalanobis distance doing? It's basically saying that let's project them, transform them linearly, transform the data points linearly to some other space, the column space of L. Then in that space, after this transformation, use Euclidean distance. So using generalized Mahalanobis distance is equivalent to transforming and then using the Euclidean distance, right? Okay, we'll continue in the next session. Thank you.